In a world where imagination refuses to stay grounded, humanity continues to build in places where construction should be impossible. Across oceans, deserts, mountains, and crowded skylines, engineers push beyond logic, gravity, and sometimes even safety itself. These are not ordinary buildings or bridges. They are bold experiments in steel, glass, and concrete, standing at the razor's edge between brilliance and catastrophe. From structures that pierce the clouds to projects that reshape entire coastlines, every one of them represents thousands of calculations, sleepless nights, and risks that could have ended in failure. A single miscalculation can mean collapse, chaos, or billions lost. Yet against those odds, these megaprojects rise, rewriting the limits of what humanity can create. Today, join us as we journey across the planet to uncover engineering feats so ambitious, so daring, and so breathtaking that even seasoned experts pause in disbelief. From towering icons to hidden technical wonders, this episode explores the next chapter of impossible construction, projects that challenge nature, redefine cities, and prove that ambition is often the strongest foundation of all. Glowing like a digital planet rising from the desert skyline, Sphere has become one of the most striking architectural experiments of the modern era in Las Vegas. Completed in 2023, the structure towers roughly 112 meters high and 157 meters wide, making it the largest spherical building ever constructed. Its exterior, known as the exosphere, is wrapped in millions of programmable LED lights that transform the entire surface into a living display, capable of showing hyper-realistic animations visible across the city. Rather than blending into the skyline, the sphere dominates it, functioning as both architecture and broadcast medium, redefining what urban landmarks can communicate visually and culturally. Constructing such a structure pushed engineers into unfamiliar territory. A perfect sphere is inherently difficult to build because conventional buildings rely on vertical and horizontal repetition, while this project required complex curvature in every direction. Thousands of steel components were fabricated with millimeter precision to form the geodesic framework supporting the outer shell. The LED system itself had to account for heat dissipation, power distribution, and maintenance accessibility, all while maintaining flawless image continuity across the curved surface. Inside, the venue houses a massive, immersive auditorium equipped with a wraparound screen exceeding 16K resolution, advanced beam-forming audio that directs sound to specific seats, and environmental effects such as vibration and scene integration, blending structural engineering with entertainment technology at a scale rarely attempted before. Operational challenges were equally demanding. Managing tens of thousands of visitors requires carefully engineered circulation paths, climate control, and acoustic isolation to prevent distortion within the spherical interior. Engineers incorporated vibration damping and structural reinforcement to maintain stability during large events, ensuring both safety and performance quality. The sphere demonstrates how modern megaprojects increasingly intersect multiple disciplines: architecture, digital media, electronics, and experiential design, creating environments that are simultaneously buildings and interactive platforms. More broadly, the sphere represents a philosophical shift in how cities create identity. Rather than serving only functional or symbolic roles, landmarks now compete for attention in a global media ecosystem. This structure turns itself into content, constantly changing, engaging audiences both physically and remotely, and reshaping expectations for entertainment venues worldwide. Standing before it, one realizes that it is less a building and more an evolving interface between technology and urban life. A glimpse into how architecture may operate in the decades ahead. where imagination and engineering merge to produce experiences as memorable as the structures themselves. Silt Aqueduct appears less like infrastructure and more like a surreal illusion, a narrow ribbon of water carried across the sky. Completed in 1805, this remarkable structure channels boats instead of vehicles, forming the highest navigable aqueduct in Britain. Stretching across the River Dee on slender cast-iron arches, it lifts canal traffic roughly 38 meters above the valley floor, offering travelers the uncanny sensation of floating at the edge of the horizon with nothing but open air beside them. Constructing such a structure more than 2 centuries ago demanded extraordinary ingenuity. Engineers faced the challenge of containing water, heavy, unpredictable, and unforgiving, within a long elevated trough that could neither leak nor collapse. The solution was revolutionary for its time: a watertight cast-iron channel supported by masonry piers and iron ribs, combining traditional materials with emerging industrial techniques. The aqueduct's narrow design minimized weight, while careful calculations ensured that both the load of the water and passing boats could be distributed evenly along its span. Beyond its technical brilliance, the aqueduct embodies the ambition of an era that sought to connect industries and communities through waterways. It stands as a testament to early industrial engineering, demonstrating how creativity and precision allowed builders to overcome the limitations of their time. Even today, crossing it remains a breathtaking experience, whether by boat gliding across its reflective surface or on foot along its towpath, reminding visitors that innovation often begins with daring ideas carried out against daunting odds. Silt Aqueduct is not simply a historical artifact. It is a living example of how engineering vision can endure for generations. Its elegant arches and suspended canal continue to inspire awe, proving that even centuries-old structures can challenge perception and redefine what humans believe possible, transforming water itself into a pathway through the sky. Stretching across a dramatic canyon in the mountainous province of Hubei, the Siduhe Bridge stands as one of the most astonishing feats of modern bridge engineering. Completed in 2009 along the G50 Shanghai-Chongqing Expressway, the bridge spans an immense gorge carved by the Siduhe River, with its deck suspended roughly 496 meters above the valley floor, making it among the highest bridges in the world by deck height. At this altitude, the structure doesn't simply cross terrain, it floats above it, transforming a once treacherous mountain journey into a seamless highway link. Constructing the bridge presented challenges that bordered on the surreal. The canyon was so deep and steep that conventional methods of stringing support cables were impossible. Engineers resorted to an unusual solution. Rockets were used to fire pilot lines across the gorge, allowing heavier cables to be pulled into place afterward. Massive towers anchor the suspension system on either side, and the main cables, composed of thousands of steel strands, support the roadway against powerful winds, seismic activity, and temperature fluctuations common to the region. Every element of the structure had to account for altitude, inaccessibility, and environmental stress, turning the project into a masterclass in adaptive engineering. Beyond its technical spectacle, the Siduhe Bridge dramatically reshaped regional connectivity. Travel that once required hours of winding through mountainous terrain was reduced to minutes, boosting economic integration and mobility throughout central China. Yet for drivers crossing its length, the experience remains breathtaking. An expansive horizon framed by steel cables and distant cliffs, a reminder of how human ingenuity can span even the most intimidating landscapes. The Siduhe Bridge is more than infrastructure. It is a testament to the relentless pursuit of solutions in extreme environments. Suspended high above a chasm once considered impassable, it demonstrates that with creativity, precision, and boldness, engineers can redefine the limits of geography itself, turning obstacles into pathways and impossibility into reality. Linking the mainland of Canada to the island province of Prince Edward Island, the Confederation Bridge is one of the longest bridges in the world to span ice-covered waters. Stretching roughly 12.9 kilometers across the Northumberland Strait, the structure permanently connected communities that once depended on ferries vulnerable to harsh winters and shifting sea ice. Opened in 1997, the bridge transformed regional mobility, allowing uninterrupted year-round travel and strengthening economic links that support tourism, agriculture, and trade in Atlantic Canada. Engineering a bridge in this environment demanded solutions rarely required elsewhere. The strait regularly freezes, and drifting ice sheets exert massive lateral forces capable of damaging conventional piers. Designers responded by shaping each pier with conical bases that break and deflect ice, reducing stress on the structure. Precast concrete segments, fabricated onshore, were transported and assembled with extreme precision, accelerating construction while maintaining durability standards suited to corrosive marine conditions. The gently curved deck also accounts for Earth's curvature and improves driver visibility, an often overlooked detail that reflects the interplay between safety and large-scale design. Beyond the technical achievement, the Confederation Bridge carries political and symbolic weight. Its name references the union that formed modern Canada, and its existence reshaped life on Prince Edward Island by removing geographic isolation that once limited development. While large infrastructure projects always spark debate, including concerns over environmental impact and financial cost, measurable outcomes show increased connectivity and economic stability in the decades since completion. Today, the bridge stands as a reminder that megaprojects are not only feats of engineering, but also catalysts that redefine how regions interact, grow, and sustain themselves in challenging natural environments. Spanning the turbulent waters of the Akashi Strait, the Akashi Kaikyō Bridge stands as a pinnacle of engineering daring and precision. Connecting the city of Kobe on Honshu with Owaya on Awaji Island, this suspension bridge boasts the longest central span of any in the world at 1,991 meters, with a total length exceeding 3,900 meters. Completed in 1998 after a decade of construction, it was designed not merely to carry vehicles, but to withstand some of the most extreme environmental challenges imaginable, including powerful typhoons, earthquakes, and intense marine currents. The bridge's design incorporates unprecedented engineering innovations. Each of the two massive towers rises over 300 meters above sea level, anchored deep into the seabed using giant caissons filled with concrete. The main cables, each composed of 36,830 high-strength steel wires, stretch for nearly 4 kilometers and are capable of supporting incredible tensile forces, ensuring stability against relentless winds and shifting tides. Engineers also had to account for seismic activity. The bridge sits near a major fault line, which required sophisticated shock absorption systems and flexibility to prevent catastrophic failure during earthquakes. Even thermal expansion and contraction of the steel over long distances were calculated with extreme precision, illustrating the meticulous attention to detail demanded by such a megastructure. Beyond its technical triumphs, The Akashi Kaikyō Bridge is a symbol of human perseverance and vision. Its construction transformed regional connectivity, reducing travel time between Honshu and Shikoku and facilitating commerce, tourism, and social exchange. Each vehicle that crosses is a testament to the hundreds of engineers, designers, and laborers who worked under harsh marine conditions, balancing ambition with safety. Standing before this immense span, one cannot help but marvel at how human ingenuity can overcome nature's most imposing challenges, turning a chaotic stretch of sea into a conduit of progress, resilience, and global engineering excellence. Yashi Expressway is often described as a highway that defies geography itself, stretching across the mountainous region between Yun and Shichong. This extraordinary route transforms a once dangerous journey into a breathtaking engineering spectacle. Suspended across valleys, threading through tunnels carved deep into rock, and weaving along sheer cliffs, the expressway appears less like a road and more like a ribbon of concrete floating above the clouds. Constructing the Yashi Expressway demanded solutions to extreme environmental, geological challenges. Engineers faced unstable slopes, high seismic risk, landslides, and heavy seasonal fog that drastically reduces visibility. To overcome this, they built hundreds of bridges and tunnels, carefully balancing structural loads while stabilizing surrounding rock and soil. Advanced monitoring systems track weather conditions and traffic flow, while protective barriers and drainage solutions mitigate hazards from falling debris and sudden rainfall. Every kilometer required precision planning, ensuring safety and durability in terrain where traditional road construction would have been nearly impossible. Beyond its technical complexity, the expressway reshaped connectivity for entire regions, dramatically reducing travel time while opening economic and cultural links between communities once isolated by mountains. Yet for travelers, the experience remains unforgettable. Sweeping curves revealing vast landscapes, elevated spans offering dizzying views, and tunnels that plunge briefly into darkness before emerging again into open sky. It is a journey that constantly reminds one of the thin line between human ingenuity and the raw power of nature. The Yashi Expressway stands as a symbol of modern engineering's ability to conquer natural barriers without erasing them. Rather than flattening mountains, it adapts to their contours, merging infrastructure with landscape in a display of bold vision and technical mastery. It proves that even in the most daunting environments, ambition and innovation can carve pathways where none seem possible, turning impossible terrain into a lifeline of movement and progress. Zhangjiajie Dam is a massive flood control and hydroelectric project built on the Yellow River in China. Completed in the early 2000s, it's best known not just for generating power, but for managing one of the world's muddiest rivers. The Yellow River carries enormous sediment loads, historically a major cause of devastating floods. So the dam periodically releases controlled torrents of water to flush silt downstream. A dramatic engineering spectacle sometimes called sand washing. The structure stands about 154 meters tall and stretches over 1.6 kilometers across the valley, combining flood control, irrigation support, water supply, and electricity generation. It's a good example of modern large-scale river management. Useful economically, but also debated because such megaprojects can reshape ecosystems, alter sediment flows, and require resettlement of local communities. Hudson Yards stands as one of the boldest urban transformations of the modern era, a place where engineering ambition reshaped land that once seemed unusable. Built above a sprawling network of active rail yards in New York City, this development represents one of the most complex construction undertakings ever attempted in an urban environment. Instead of building on solid ground, engineers created an enormous platform supported by massive steel trusses and reinforced concrete, proving that even the busiest transportation infrastructure beneath could coexist with towering skyscrapers and public spaces above. The challenges were immense. Designing foundations capable of distributing weight without disrupting the rail lines required precision engineering and meticulous planning. Temperature fluctuations, vibration from trains, and wind loads on high-rise towers had to be accounted for long before construction began. Glass-clad skyscrapers now rise confidently from this artificial base, housing offices, residences, and observation decks, each relying on structural systems built to absorb motion and resist stress in one of the densest urban environments on Earth. At the center of the development sits its most visually striking attraction, Vessel, a honeycomb-like network of staircases that spirals upward in geometric symmetry. While artistic in purpose, its construction demanded careful load calculations and material precision, as thousands of visitors climb its interwoven pathways daily. Nearby, the dramatic sky deck, extending from a tower, offers sweeping views high above the city, reinforcing the idea that Hudson Yards is not just architecture, but an experience engineered to challenge perspective and scale. Hudson Yards ultimately represents more than real estate or skyline aesthetics. It demonstrates how modern engineering can reclaim and redefine space, once considered impractical, transforming industrial infrastructure into a thriving vertical neighborhood. Walking through it, one witnesses the convergence of planning, design, and structural innovation, a reminder that even in cities where space is scarce, human ingenuity continues to expand what is possible. International Space Station is one of humanity's most extraordinary engineering achievements, not because it sits on land or spans a river, but because it orbits roughly 400 kilometers above Earth at about 28,000 kilometers per hour. Built through an unprecedented partnership led by agencies including NASA, Roscosmos, European Space Agency, JAXA, and Canadian Space Agency, the station represents decades of international cooperation in science, technology, and exploration. Since the first modules were launched in 1998, astronauts and cosmonauts have continuously lived and worked aboard it, making it the longest-running human presence in space. The station itself is a modular structure assembled piece by piece in orbit, a process requiring dozens of missions and countless spacewalks. Solar arrays stretching wider than a football field generate electricity, while interconnected pressurized modules house laboratories, living quarters, and observation windows. Inside microgravity conditions, researchers conduct experiments impossible on Earth, studying everything from fluid physics and combustion to human bone density loss and advanced materials manufacturing. These experiments aren't just academic. They inform medicine, engineering, and long-duration mission planning for future travel beyond low Earth orbit. Operating the ISS is a constant balancing act between innovation and risk. Crews must manage radiation exposure, extreme temperature shifts outside the hull, and the ever-present threat of orbital debris traveling at hypersonic speeds. Regular maintenance and periodic boosts for visiting spacecraft keep the station stable in orbit, highlighting how sustaining life in space requires relentless technical oversight. Despite these challenges, the ISS has served as a testing ground for technologies that could one day support missions to the Moon, Mars, and beyond. More than just a laboratory, the International Space Station stands as a symbol of what global collaboration can achieve when political and scientific interests align. It demonstrates that megaprojects are not confined to Earth's surface. Some of the most complex structures humanity has built circle the planet itself, quietly advancing knowledge while visible only as a bright moving point of light crossing the night sky. Deep inside a frozen mountain on a remote Arctic island lies one of humanity's quietest yet most critical insurance policies, the Svalbard Global Seed Vault. Located on the Norwegian archipelago of Svalbard and operated in partnership with the government of Norway and organizations like the Crop Trust, this facility was designed as a global backup for the world's agricultural biodiversity. Opened in 2008, it stores duplicates of seeds from gene banks worldwide. Not for immediate use, but as a last resort safeguard against disasters ranging from war and climate collapse to crop disease or systemic food failure. The vault's engineering is deceptively simple yet highly strategic. Carved deep into permafrost, it sits hundreds of kilometers from major population centers and well above sea level to protect it from flooding, even under worst-case climate projections. Thick concrete walls, blast-proof doors, and naturally low Arctic temperatures keep the interior stable at around minus 18 degrees Celsius, the ideal environment for preserving seeds for decades or even centuries. Even if mechanical cooling systems fail, the surrounding frozen ground slows temperature changes, creating passive resilience rarely matched by other storage infrastructures. Inside, more than 1 million seed samples representing thousands of crop species are sealed in packages and stored on metal shelving. Each deposit comes from national or regional seed banks, meaning ownership stays with the depositing country while the vault functions purely as secure storage. Its purpose became tangible when the International Center for Agricultural Research in the dry areas withdrew seeds after conflict damaged its Middle Eastern facilities, demonstrating that the system isn't symbolic, it's operational and necessary. Genetic diversity preserved here underpins global food security, enabling scientists and farmers to restore crops lost to changing climates, pests, or catastrophe. What makes the Svalbard Global Seed Vault remarkable isn't its scale or visual spectacle, but its long-term perspective. Many megaprojects solve immediate needs, yet this one anticipates threats that may unfold over centuries. It reflects an acknowledgement backed by data that global agriculture depends on a narrow genetic base and that biodiversity loss increases systemic risk. In that sense, this Arctic repository is less a monument and more a contingency plan for civilization itself, quietly protecting the biological foundation of human survival beneath the ice. Stretching across the Detroit River, the Gordie Howe International Bridge represents far more than a transportation link. It's a modern symbol of economic integration between Detroit and Windsor, and by extension between the United States and Canada. Named after hockey legend Gordie Howe, the bridge is designed to relieve congestion at one of North America's busiest commercial border crossings, where billions of dollars in goods move annually. When fully operational, it is expected to significantly streamline trade routes that are critical to automotive manufacturing, agriculture, and industrial supply chains on both sides of the border. From an engineering standpoint, the structure stands out as one of the longest cable-stayed bridges in the region, with a main span exceeding 850 meters. Its twin pylons rise dramatically above the river, supporting a deck built to carry multiple lanes of traffic, pedestrian pathways, and customs-linked infrastructure integrated into the approach systems. Constructing such a crossing required careful coordination of binational regulations, environmental assessments, and river navigation concerns, highlighting how megaprojects often face as much diplomatic and logistical complexity as technical challenge. Materials, wind loading tolerances, and ice flow considerations were all factored into the design, reflecting the harsh seasonal conditions common to the Great Lakes corridor. Beyond the physical structure, the bridge's strategic importance lies in resilience and redundancy. Previously, cross-border commercial traffic in this corridor relied heavily on a single aging link, creating a potential bottleneck with measurable economic risk. Diversifying crossing capacity reduces vulnerability to disruptions and strengthens continental logistics networks. A real-world reminder that infrastructure isn't just about moving vehicles, but about safeguarding supply chains that support millions of jobs and trillions in trade value. In that sense, the Gordie Howe International Bridge isn't simply another span of steel and concrete. It's an investment in stability, cooperation, and long-term economic continuity across one of the world's most interconnected borders. Crossing some of the harshest terrain on Earth, the Qinghai-Tibet Railway is often cited as one of the boldest rail engineering projects ever attempted. Extending from Xining to Lhasa, the line climbs onto the vast Tibetan Plateau, a region frequently called the roof of the world. Built under the direction of China Railway Engineering Corporation and completed in stages before opening fully in 2006, the railway connects remote high-altitude regions to national transport networks, reshaping accessibility and economic development across Western China. The challenge wasn't distance alone, it was altitude, climate, and geology. Large portions of the route sit above 4,000 meters, with the highest track at over 5,000 meters near the Tangula Pass. Oxygen levels here can drop to roughly 50 to 60% of those at sea level, affecting both workers during construction and passengers afterward. To mitigate this, trains include pressurized cabins and onboard oxygen systems, while stations along the route were designed with medical and acclimatization considerations in mind. Another major obstacle was permafrost. Thawing ground could destabilize tracks. Engineers developed elevated track beds, heat-reflective materials, and cooling ducts to maintain ground stability. Innovations that pushed railway design into new territory. Environmentally and politically, the railway remains debated, reflecting the complex trade-offs often tied to megaprojects. Supporters highlight improved mobility, tourism, and logistics, citing measurable increases in regional connectivity and economic integration. Critics raise concerns about ecological disruption and cultural impact, emphasizing that infrastructure of this scale inevitably reshapes landscapes and societies. Objectively, both views rest on observable outcomes. Infrastructure expands opportunity, but also alters local dynamics, making the railway an instructive case study in how engineering decisions ripple far beyond technical achievement. Today, the Qinghai-Tibet Railway stands not just as a transportation link, but as a demonstration of human capability to build under extreme environmental constraints. It illustrates how megaprojects can redefine what's physically possible while simultaneously forcing broader conversations about sustainability, adaptation, and the long-term consequences of connecting previously isolated regions. Rising from the sands of the Egyptian desert with an aura of timeless mystery, the Great Pyramid of Giza stands as one of humanity's most extraordinary and enduring architectural achievements. Constructed over 4,500 years ago during the reign of Pharaoh Khufu, it was originally intended as a tomb, yet it transcends its funerary purpose, symbolizing the ingenuity, ambition, and organizational skill of ancient civilizations. Composed of roughly 2.3 million limestone and granite blocks, each weighing between 2.5 to 3 tons, the pyramid rises to approximately 146 meters and was the tallest human-made structure on Earth for millennia, a feat that still inspires awe in engineers and archaeologists alike. The construction techniques remain a subject of debate and fascination. Without modern machinery, workers transported massive stones using sledges, ramps, levers, and ropes, while sophisticated surveying methods ensured precise alignment with the cardinal points. Scholars estimate that tens of thousands of laborers, carefully organized into teams, worked for decades to complete the project. The interior passages, chambers, and shafts reflect an advanced understanding of geometry and structural load management, allowing the pyramid to remain stable despite its immense weight and the passage of time. Its construction challenged not only human stamina, but also the limits of ancient engineering knowledge. Beyond its technical brilliance, the Great Pyramid of Giza serves as a testament to the societal and cultural organization of the Old Kingdom. The ability to mobilize resources, coordinate labor, and sustain supply chains on this scale suggests a level of planning and administrative sophistication that rivals modern projects. Additionally, the pyramid's alignment with celestial bodies, including the North Star and specific solar events, highlights a deep understanding of astronomy, reinforcing the idea that its creators sought harmony between the terrestrial and the cosmic. Even today, the Great Pyramid captivates the imagination, drawing millions of visitors and inspiring countless studies. It is not only a marvel of ancient engineering, but also a symbol of human ambition, a reminder that creativity, organization, and determination can overcome enormous challenges. Standing before it, one cannot help but feel the weight of history and the extraordinary achievement of a civilization that dared to reach for the heavens, leaving a structure that has endured as both a monument and a mystery for thousands of years. Spanning thousands of kilometers across western China, the Taklamakan Desert is often called the Sea of Death, a vast expanse of shifting sand dunes, brutal heat, and arid plains that has challenged travelers for centuries. Stretching roughly 1,000 kilometers east to west and covering an area of about 337,000 square kilometers, it is one of the largest sandy deserts in the world, and its inhospitable conditions have made every crossing a formidable feat of endurance and planning. Yet despite its harshness, modern engineering has transformed human interaction with this forbidding landscape, connecting settlements, trade routes, and resources that were once isolated by the sheer scale of nature. Historically, the desert was a barrier along the ancient Silk Road, with caravans risking dehydration, sandstorms, and extreme temperature fluctuations to move goods between east and west. Today, modern highways, railways, and pipelines traverse this vast terrain, including sections of the Taklamakan Desert Highway, which required innovative construction techniques to prevent roads from being buried by shifting sands. Engineers used stabilizing sand barriers, gravel layers, and carefully designed embankments to ensure that infrastructure could endure the relentless wind and moving dunes. Water scarcity, extreme summer heat exceeding 40 degrees Celsius, and freezing winter temperatures demanded durable materials and constant maintenance. A true testament to human ingenuity confronting nature at its most extreme. The Taklamakan Desert is more than a natural obstacle. It is a laboratory for adaptation, planning, and survival. Modern projects in the region, from transport corridors to energy pipelines, illustrate how careful engineering can turn seemingly impossible terrain into functional space. Yet the desert retains its wild majesty. Sand seas shift overnight, mirages appear on the horizon, and ancient trade routes whisper the stories of travelers who dared to cross it centuries ago. In a world dominated by urban megastructures and towering bridges, the Taklamakan reminds us that even landscapes, not just steel and concrete, can present engineering challenges that test the limits of human ambition. It is a place where survival, innovation, and the raw power of nature converge, offering a humbling perspective on scale of our environment and the audacity required to tame it. Rising as a monument to human resilience against the relentless forces of the sea, the Delta Works stretches across the southwestern coast of the Netherlands, safeguarding a nation historically vulnerable to flooding. Born from tragedy, the devastating North Sea storm of 1953, which claimed over 1,800 lives and submerged vast stretches of farmland. The Delta Works is not a single structure, but a massive network of dams, sluices, locks, dikes, and movable storm barriers designed to control the flow of water from the sea into the low-lying delta region. Over decades, it has transformed the Dutch coastline, effectively shortening vulnerable stretches from hundreds of kilometers to a fraction of their former length, all while maintaining navigable waterways for commerce and transportation. The engineering feats involved in the Delta Works are nothing short of extraordinary. Movable barriers like the Maeslantkering can swing into place to protect against storm surges, while massive sluice gates control water levels with precision across interconnected estuaries. Each component had to be carefully modeled and tested, considering extreme tides, storm frequency, soil subsidence, and the long-term impact of climate change. Advanced hydraulic systems, reinforced concrete, and innovative construction techniques allowed engineers to build structures that could withstand immense pressure from the North Sea, while also being adaptable to future environmental conditions. A rare blend of strength, flexibility, and foresight. Beyond the technical accomplishment, the Delta Works represents a national commitment to living with water rather than simply fighting it. The project integrates ecological considerations, allowing tidal flows in certain areas to sustain wetlands and marine habitats, while also ensuring safety for millions of residents and protecting economic infrastructure. It has become a model for coastal engineering worldwide, demonstrating how science, planning, and human ingenuity can transform a landscape once considered perilously unstable into one of security and sustainability. Standing before the Delta Works today, one sees more than concrete and steel. It is a testament to the Dutch mastery of water, the ability to plan for centuries ahead, and the enduring spirit to protect life and livelihood from one of nature's most persistent threats. It reminds us that the most ambitious megaprojects are not always about vertical height or record-breaking spans. Sometimes, their greatest impact is measured in the lives they save and the landscapes they preserve. Perched on the sun-drenched coast of Chile, San Alfonso del Mar is a striking example of human ambition transforming leisure into a feat of engineering. Opened in 2006 in the seaside town of Algarrobo, the resort is home to the world's largest man-made swimming pool, stretching over 1,013 meters and covering nearly 20 hectares, holding more than 250 million liters of crystal-clear seawater. Beyond sheer scale, the pool represents a marriage of cutting-edge technology, environmental management, and aesthetic vision, making it one of the most visually stunning and technically impressive leisure facilities ever constructed. Engineering the pool required solving challenges rarely encountered in conventional construction. To maintain its enormous volume of water, engineers devised a filtration and circulation system capable of moving 66 million gallons daily, ensuring the water remained clean, clear, and safe for swimmers. The design also accounts for ocean water replacement and temperature regulation, while preventing structural stress and leaks over such unprecedented distances. Surrounding the pool, high-end residential towers, landscape gardens, and recreational facilities were strategically integrated to offer both panoramic ocean views and seamless access to the aquatic centerpiece, demonstrating meticulous urban planning at resort scale. San Alfonso del Mar is more than a pool. It's a destination that reshapes expectations of human interaction with natural landscapes. The lagoon allows kayaking, sailing, and other water sports in a controlled environment, while preserving the aesthetics of the coastal terrain. Its success reflects both technological mastery and visionary design, illustrating how ambition and innovation can turn a natural resource, the sea, into a monumental recreational experience without entirely replacing the environment it inhabits. Today, the resort stands as a symbol of bold thinking in civil and leisure engineering, where human creativity transforms scale into spectacle. It reminds us that megaprojects need not only serve utility or industry. Some are built purely to inspire awe, providing a glimpse of how far design, technology, and imagination can push the boundaries of possibility. The Avenue high-speed rail is Spain's crowning achievement in modern rail travel, connecting major cities like Madrid, Barcelona, and Seville at speeds exceeding 300 kilometers per hour. Launched in 1992, the Avenue transformed transportation across the Iberian Peninsula, drastically reducing travel times and linking regions once separated by long, arduous journeys. Its sleek, aerodynamic trains glide along dedicated tracks, crossing rivers, plains, and mountains with precision and efficiency, demonstrating how high-speed rail can combine speed, comfort, and environmental sustainability. Beyond its performance, the Avenue network represents a feat of engineering. Bridges, tunnels, and viaducts were constructed to maintain straight, level tracks required for such high speeds, while advanced signaling and control systems ensure safety even at full velocity. The network has reduced reliance on cars and short-haul flights, lowering carbon emissions and promoting regional connectivity. The Avenue is more than a train. It's a symbol of how modern infrastructure can reshape mobility, economy, and lifestyle, proving that even in sprawling landscapes, distance can be conquered with precision, planning, and technology. Rising sharply from the skyline of Chicago, the Willis Tower, formerly known as the Sears Tower, is an enduring icon of architectural ambition and engineering mastery. Completed in 1973, this 108-story marvel stood as the tallest building in the world for over 2 decades, reaching a staggering height of 442 meters to its roof, or 527 meters, including its antennas. Beyond its sheer vertical scale, the Willis Tower represents a triumph of structural innovation, where bold design and practical engineering merged to redefine what was possible in urban construction. The tower's distinctive bundled tube design, conceived by structural engineer Fazlur Rahman Khan, allows for both strength and flexibility, enabling the building to withstand fierce winds and the seasonal thermal stresses of the Midwest. Each of the 9 interconnected tubes rises to varying heights, distributing weight and reducing swaying at extreme elevations, while advanced elevators zip visitors from street level to sky-high observation decks in seconds. The sky deck on the 103rd floor, including the glass-floored ledge, offers panoramic views of Chicago and Lake Michigan, giving millions a literal and metaphorical perspective on human ambition towering above the cityscape. Constructing the Willis Tower demanded meticulous planning, precision, and innovation. From fabricating high-strength steel components to managing complex logistics in a dense urban environment, engineers and builders overcame immense challenges. Its impact goes beyond architecture. The tower transformed Chicago's global identity, inspiring both urban development and public fascination with skyscrapers. Today, the Willis Tower is more than a building. It's a symbol of human ingenuity, resilience, and the audacity to reach ever higher, reminding us that the skyline is not just a backdrop, but a testament to the dreams and determination of those who dared to build it. Soaring above the banks of the Mississippi River, the Gateway Arch stands as a shining symbol of America's westward expansion and engineering ambition. Completed in 1965 in St. Louis, the arch rises to an astonishing height of 630 feet, 192 meters, making it the tallest man-made monument in the United States. Designed by architect Eero Saarinen, its sleek, stainless steel, inverted catenary curve is both elegant and structurally remarkable, exemplifying the marriage of form and function in modern engineering. Constructing the Gateway Arch presented unprecedented challenges. The 2 legs of the monument, each composed of triangular sections of steel presence transformed the St. Louis skyline, attracting millions of visitors from around the world who marvel at its scale, design, and the breathtaking panoramic views of the Mississippi River and cityscape from its observation deck. The Gateway Arch is more than steel and concrete. It is a triumph of visionary design, technical precision, and the enduring human desire to create monuments that inspire, commemorate, and endure across generations. Suspended high above the lush valleys of Zhangjiajie National Forest Park, the Zhangjiajie Glass Bridge redefines both thrill and engineering. Opened in 2016, this breathtaking structure stretches 430 meters across a deep canyon and hangs 300 meters above the forest floor, offering visitors an unparalleled view of the towering sandstone pillars that inspired the landscapes in movies like Avatar. More than a tourist attraction, the bridge is a masterclass in precision engineering, demonstrating how human ingenuity can create safe yet heart-stopping experiences in extreme natural environments. The construction of the bridge required extraordinary innovation. Engineers had to design a deck capable of supporting thousands of visitors simultaneously while remaining transparent and visually seamless. The steel frame, combined with multiple layers of tempered glass panels, ensures both strength and resilience against wind, temperature fluctuations, and seismic activity. Each glass panel is engineered to withstand several tons of weight, giving visitors the sensation of walking on air without compromising safety. Vibration dampers, high-tension cables, and reinforced anchor points were meticulously calibrated to keep the bridge stable despite the forces of gravity and the natural sway caused by human traffic. Beyond its technical achievements, the Zhangjiajie Glass Bridge represents a bold vision for tourism and architectural spectacle. It allows visitors to intimately experience the dramatic verticality of the park, bridging extreme natural beauty with human creativity. The bridge has not only become a global icon of area design, but also a symbol of how modern engineering can transform a landscape into an unforgettable experience, blending safety, innovation, and sheer awe-inspiring scale. Walking across it, one cannot help but feel both the fragility and the power of human ambition suspended high above the earth. Rising like a vision pulled straight from tomorrow's imagination, the Museum of the Future dominates the skyline of Dubai as one of the most unconventional structures of modern architecture. Opened in 2022, the building's torus-shaped form, a gleaming oval ring with a hollow center, symbolizes humanity's continuous pursuit of knowledge and innovation. Its stainless steel facade is etched with flowing Arabic calligraphy, illuminated at night, blending cultural identity with futuristic design and turning the structure itself into a living statement about progress and imagination. Constructing this landmark pushed engineering far beyond traditional methods. Unlike typical towers built on repeating floor plates, nearly every panel of the building's outer shell is unique, requiring advanced parametric design and robotic fabrication. More than 1,000 precisely manufactured steel and composite panels form the curved envelope, demanding digital modeling tools capable of translating complex geometry into buildable reality. Inside, column-free exhibition spaces were achieved through a sophisticated structural frame that distributes loads through the ring, allowing immersive installations without obstruction. Even the facade functions as more than decoration. It manages heat, light, and energy efficiency in the harsh desert climate, integrating sustainability into spectacle. Yet the museum's significance extends beyond its engineering triumph. Dedicated to exploring emerging technologies, climate solutions, and future societies, it reflects the ambition of Dubai to position itself at the forefront of innovation and global dialogue about tomorrow's challenges. Visitors move through interactive experiences designed to provoke thought about space exploration, artificial intelligence, and environmental resilience, transforming architecture into narrative, a place where structure and storytelling merge seamlessly. Standing before the Museum of the Future, you witness more than a building. You encounter a statement about possibility. It demonstrates how architecture can transcend function, becoming both symbol and laboratory, reminding us that the boldest megaprojects are those that challenge us not just to build bigger, but to imagine further. Carved silently beneath the restless waters of the English Channel, the Channel Tunnel stands as one of the most ambitious infrastructure projects ever attempted between the United Kingdom and France. Stretching roughly 50 kilometers, with about 37 kilometers running underwater, it is the longest undersea rail tunnel in the world. Opened in 1994 after years of planning and construction, the tunnel permanently connected the British Isles to mainland Europe by rail, transforming trade, travel, and cultural exchange. What once required ferries or flights could now be traversed in minutes beneath the seabed, a triumph that many once considered impractical or even impossible. Constructing this passage demanded precision on a historic scale. Teams bored from both sides simultaneously using giant tunnel boring machines, navigating through chalk marl rock chosen for its stability and low permeability. Meeting beneath the seabed required alignment accuracy measured in centimeters, a testament to advanced surveying and engineering coordination. The project ultimately created 3 parallel tunnels, 2 rail tunnels, and a central service tunnel used for maintenance and emergency access. Engineers also had to address ventilation, fire safety, and pressure control in an enclosed environment carrying high-speed trains, integrating redundant safety systems that continue to set standards for modern tunnel infrastructure. Beyond its engineering complexity, the Channel Tunnel reshaped economic and social connections across Europe. Freight flows became faster and more efficient, tourism surged, and the psychological barrier of sea separation diminished. Yet its creation was not without controversy. Financial overruns, political negotiations, and technical challenges tested both governments and contractors. Still, its successful completion demonstrated how cooperation and technological innovation can overcome geographic obstacles once thought insurmountable. Today, the Channel Tunnel is more than a transportation corridor. It is a symbol of persistence, collaboration, and engineering confidence. It reminds us that megaprojects are not only about conquering nature's barriers, but also about redefining how societies connect. Beneath layers of rock and ocean water, steel rails carry millions of passengers and tons of goods each year, quietly proving that some of humanity's boldest achievements remain hidden from view, yet profoundly shape the world above.